classical mechanics, Lagrangian mechanics, the jiggle pendulum. That's where we're at. So playlist down below in case you're just joining in. You can catch all of my classical mechanics videos for this semester. But you did it too, we did it together, the jiggle pendulum. So a jiggle pendulum is like a normal pendulum, except the top point moves up and down, so that the position of the top is a sine omega t. Now, to do Lagrangian mechanics here, we only need 1 degree of freedom, one variable theta. But you know, as always with Lagrangian mechanics, the struggle is getting the kinetic energy term, and so we do that by making a relationship to Cartesian coordinates, because I know in Cartesian coordinates I can write down the kinetic energy 1/2 m x dot squared plus 1/2 m y dot squared. And if I can take those derivatives, and I know the variable theta is in there, and I'm going to have t, then I can write it in terms of t and theta dot. And that's the thing, and that's we did that. Here's part of that work. I'm not going to redo the whole solution, but then we can apply the Lagrange's equation. So let me just erase what I have up here and write down the key steps. And we're not going to do those steps because the algebra wasn't bad. It wasn't bad, but it wasn't super easy either, right? There was easily a chance to make a mistake. So I'm going to show you how to use Python to do the algebra. And, you know, it's not cheating, okay? It's checking. So let's just go over the big ideas again about what steps we need to do, because we're going to do those steps in not Web v Python. We're going to do them in Jupyter notebooks using some other modules. Grown-up Python, which I normally like the Web v Python better, but okay. So we have this. We have 1 degree of freedom. I can write x and y in terms of theta and time. And then I can write the Lagrangian as t minus u, where t is 1/2 m x dot squared plus y dot squared, and u is mgy in this case. Okay, so to do those, I need to take the derivative, I need to square it, I need to add them together. Once I do that, I can write down Lagrange's equation, the partial of L with respect to theta minus the time derivative of the partial of L with respect to theta dot is equal to 0. And then from that, what I did was I solved for theta double dot, and I got an expression. And then we solved the problem numerically. So to solve it numerically, I assume a time step of delta t of 0.01 seconds. And during that time interval, I'm going to assume whatever calculation I get for theta double dot is constant. So theta double dot is delta theta dot delta t. So theta 2 dot theta 1 dot plus theta double dot delta t. So this is a way to update my angular velocity, my theta dot. So this is theta dot 1 is at the beginning of the time interval, and that's at the end. So I need to update that. And then I can do the same thing with theta 2, theta 1 plus theta 2 dot delta t, and then just keep doing it over and over again. And we're going to do that. We're going to do this in real Python. It's going to be great. But solving this stuff is algebraically not bad, right? But you could make a mistake. I can make a mistake. I have made mistakes. I will make mistakes. So the first thing I want to do is to jump back into Web v Python, the solution that we already had, and I want to plot the position, the angular position as a function of time, just so we can have something, a reference point. Okay. So I didn't switch over here. You're still looking at me. So here we are. This is the program that I had before. The link is in the previous video. It's in that playlist. So I hope you can find it. But if you don't know, ask questions. I answer questions. Okay, so I have some initial conditions. I'm going to use the same ones, and I'm going to run this. And if I get the same graph, then it assumes those two methods are the same. And this is an important thing when you're learning something new. Do it on something you know so you know if you're doing it right. Okay, so I'm going to run this. Here's my jiggle pendulum. We can watch it if you want, jiggling, right? It's kind of cool. We could do the inverted thing too, but I'm not going to do that. And then I have that plot right there. So that's what I want to reproduce. Okay, now let's just get into it now. So here I have a Jupyter notebook. So if you're not familiar with Jupyter notebooks, first you have two options, and I'll link these both down below. You can install it, on your computer for free, and it'll load all the appropriate modules and all that stuff. But also, there's an online version, Google Colab. If you search for Google Colab, you can do it in a web page, and it runs on Google servers, which is kind of nice because it works on like a tablet and stuff, so you don't have to install anything. Technically, it works on your phone. Okay, let's just get to it. One of the things, there's a couple of important points about Jupyter notebooks. One is this idea of a cell. So these cells are individual codes of blocks of code that you can run individually. I'm not going to go over that too much. You could even write text in there, but I'm not going to do that. Okay, so I'm not doing a Jupyter notebook thing. Now, the other thing though is that in this Python, things aren't loaded for us. So we have to load whatever modules we want. And there's 3 that we're going to need. I'm going to go ahead and load them. So to load a module, I'm just going to say import Sympy. So that's symbolic Python. But if you want to call it Sympy, that's cool too. Okay, as SP. So what we do is we don't just import that module, we give it a short name so that when I'm calling on functions from a particular module, I refer to them by that name so I can know which module to get which thing from. I'm going to need NumPy. Again, you could call it NumPy. Most people call it NumPy. NumPy is just fun. And that's, so Sympy has all of our symbolic algebra functions in there. NumPy has our numerical functions in there. Now, I need one more thing. Import matplotlib.pyplot as plt. So that's going to be used for graphing. Now, you could import Sympy as Bob. You could say up here, Bob. And my students sometimes like to do that because they think it's funny. Okay, that's fine. But don't copy down code later and use SP instead of Bob. You're going to have an error. I'm just saying, just do what everyone else does. Okay, so I'm going to run this cell. I like to run that cell just to make sure things are working. And there we have my little star that tells me that it is indeed running at this moment. It's still running. Okay, there it's loaded. Okay. Now, in Sympy, what we need to do is to use algebraic variables, symbolic variables. But we need to tell Sympy what those symbolic variables are. So we have a bunch that don't really matter that much that we're just going to treat as variables. Time, G, mass, the radius of the string, which I call R, the amplitude of oscillation A, and the angular velocity of the oscillation omega. So I'm just going to declare all those variables. So I have, let's see if I can remember them. T, A, G, R, omega, M. I think that's it. Yeah, and that's going to be of a type sp.symbols. Now I can over here tell it how to display those symbols, right? So that doesn't make much. T, A, G, R, aha, omega. I'm using the latex version of omega so that it will actually put it as omega. That's kind of cool. And you don't need to put commas there. That's all you need to do. Okay, now there's another variable that I need. I need theta, but theta is not just a normal variable. Theta is a function of other variables, so I need to tell Sympy that. So here's my theta. It's sp.symbols. Again, got to spell it right. Symbols. Now I'm going to write this. I'm going to call it theta, which is the latex version of the word theta. And then that R there is important because that says do this as raw text, because a lot of times when you put in the text, that slash means return, and this says don't do that. We're going to use just a slash, I think. I want to make a statement about Python, especially stuff like this. You know, you go and you see, I was thinking of Lord of the Rings, but no, some other fantasy movie or Dungeons and Dragons, and you have a wizard, and the wizard has scrolls, right? Because they can't memorize everything and how to do stuff, so sometimes they just read off those scrolls. That's like these modules. Sometimes it's just magic, and you got to remember the magic code word so that you can use the spell. And this spell is to solve algebra. Is that a bad analogy? I don't know. I like it. Okay. So it's also, I need to say it's a class of a function. So sp.function. So that tells it it's going to actually be a function, and I can declare what that function is. So I'm going to say theta is theta of t. So it looks just like a math function. Okay. So let's just run this. I'm going to say this theta just so you can see. There. See, so if I just, and I print it, don't print theta, just say theta. So theta is an object in Sympy. And so it ran it, and it gave me this nice little theta as a function of t. That's kind of cool, right? We're already doing cool stuff. Okay, now I'm going to need some other variables. I need theta dot, and that's the derivative of theta with respect to time. And I've already said theta is a function of time. So that's going to be sp.diff for differential theta t. So it says take the derivative of the function theta with respect to time, and that's called theta dot. You could call it whatever you want. And then I could say theta double dot. I use dd dot. You use what you want. It's going to be sp.diff theta dot t. And let's just run that theta double dot and see if it makes sense. Made sense. Works. Isn't that nice? Okay. So we're moving right along here. Now that I have theta dot, theta double dot, I can define my x and y variables, which is what I want, right? So from before, and I have it on the board, and go back and look at this, x is going to be r times sp dot sine theta. So if you've been using Web v Python, so sine is a function that's built in, but it's not built in Python. And there are two signs. There's an numpy sign, which gives you a numerical value, and then there's a symbolic sign, which gives you a symbolic sign. So you want to use a symbolic one. Okay. Now I can do y, just like before, it's going to be a times sp dot sine, that's right, sine omega times t minus r times cosine theta. That's right? Yeah, okay. Except sp. So now I have x and I have y. Now I can write the kinetic energy term, and then I'll print that, just so you see what it looks like. It's nice to run this and then add and run and add and run, just so you can kind of make sure you're on the right track. So t, and I'm going to do this two ways. T is 1/2 times m times, I'm going to put this in parentheses, x dot squared. So that means I'm going to take the derivative of x, which is sp dot diff xt. I need to square that. And then I'm going to add sp dot diff yt. I'm going to square that. And then let's print this. And there you go. So there's my kinetic energy term. It looks kind of not nice. And one of the things I'm going to fix right here is this 0.5. So I did 1 divided by 2. That's a numerical. Those are numbers. So it's like, fine, do numbers. If you want to write it, because you do, because if we want to print this out for something to put on a test or something, I want this as sp.rational, rational 1, 2. So it's going to use the rational function 1 divided by 2. And if I run that this time, now I get that overall 1/2. And if you really want to, maybe this simplifies some. I can simplify it. T dot simplify. It doesn't really matter. Simplify. And it looks a little bit better, maybe not much. Who cares? Oh, you can't even see that. Look at that. Okay. And you can't even see the end. Don't worry, it's there. Okay, I'm focusing on the code. Okay, now I need u. U equals m times g times y. That's it. I don't need to tell it what y it is. Y's already there. Just like I didn't need to tell it how to take a derivative of x. It did it. And it got all in terms of theta and theta dot. Cool. Okay. So L is going to be t minus u. If you want to print this, we can. Let's just do L dot simplify just to see if things are working. And that will be great. Okay. It seems okay. Okay. Sorry, my nose itches. Okay. So now what I want to do is to create the Euler-Lagrange equation and solve that. So I need to take the derivatives and stuff like that. So one of the things that that we have here is we can create this as a differential equation equal to 0. So Sympy likes things equal to 0. So we're going to make this thing called LE. It's the Euler-Lagrange equation if you want. And it's going to be equal to, I'm just going to type in the partial of L with respect to theta minus the derivative of the partial L with respect to theta dot. I'm going to write that as an equation. So that's going to be sp dot diff L, which I have, with respect to theta. That's that first term, minus sp dot diff L theta dot t. So this right here is the derivative of L with respect to theta dot, and then the other stuff is the derivative of that with respect to t, so it is the same thing. Of course, we want to print that. Le dot simplify, I mean, we did that before. We did it in real life. Okay, that looks pretty good, right? And that's really what we want. And now, we do want to solve this. We could stop here. We could take that and use it for what we want. It looks a little bit different than what we had, but that's fine. But what we wanted to remember was to solve this for theta double dot. And you see it's right there, theta double dot. Second derivative of theta with respect to time. Now, that's not hard. It could be hard though. So we can actually solve this for theta double dot with Sympy too. So let's call this, I'm just going to call it sols for solutions, because it normally would return a dictionary of multiple results, because you could have more than one equation. We just have one equation, one unknown. Our one unknown is theta double dot. So I'm going to say sols LE for theta double dot. And then let's just do sols dot simplify. That won't work. It's actually a list of 0 things, so I have to do sols 0 dot simplify. Simplify. Okay. And I made a mistake. Okay, where did I make a mistake? Oh, I'm sorry. Sols equals, that was stupid. Sols equals sp.solve. Yeah. And you'll notice that's pretty much what we got before. It's a little bit different format. And most importantly, when the same check we had before, if a is equal to 0, it should be a pendulum. So if a is 0, that term goes away and I get negative g over r sine theta. Boom. So it looks like it works. Okay, we could just stop here and say, okay, we have the solution. But I want to go ahead and plot the solution in Jupyter notebooks because I want to. Now, there are multiple ways to solve a differential equation in Sympy and NumPy. I'm going to do the way that matches up with Web v Python. So we're going to do the same thing. T is 0, dt is, I had 0.001, and the same values, and then break it into small time steps. And there's really going to be mostly the same code, except for one difference. So, and even then, there is another way you can do it with lists, with arrays, but I'm not going to do that today. If you want to do that, we can do that later. So let's just go back over to Web v Python. And I want to get the same values because I don't want to type it. So let's just type all this stuff, all that stuff. Copy that, and then go back over here and paste that. Okay, now we are going to do something that is a bad idea, but life is full of bad ideas. The bad idea is that I'm going to reuse these variables g. I already said g was a symbol. Now I'm saying g is 9.8. Python's like, if you want to do bad things, you do bad things. And I want to do bad things. Okay, so that's fine. So I have g, r, a, omega, t, dt, theta. Now here's a problem right here because I have pi, but pi is not built in, so I'm going to say np dot pi. Okay, theta dot right there. So that should be good. Now, I'm going to go through a loop, and I'm going to do the exact same thing I did before. Now, up here, one thing I want to do is to print this out as a thing. So I'm going to delete this right there. I'm going to print it. I'm going to print sols. And you'll see something different. We get this as an expression, so I can copy and paste that and reuse that. So let's go down here, and I'm gonna make 2 lists: TP for plotting time, and theta p for plotting theta. And this is because Web v Python, we actually plot one point at a time, but matplotlib wants you to give it all the data together and then plot it. It doesn't want to be coming back and forth, just one thing. So I'm going to make a list of all my time values. I'm going to make a list of all my theta values, and then I can add them that way. And so we can go ahead and add in our first value, 0, and this is going to be equal to this. So it's not an empty list. Now I'm going to say while, and you can't even see that, while t less than 4, which is what I did. And I'm not going to do a rate statement because I'm not animating anything. And the first thing I want to do is calculate theta double dot. Theta dd dot equals. Now here's where this comes into play. I can copy that and paste it. I don't want to retype it. Typing's for barbarians, right? Okay, but I do need to fix some things because right here it says the omega, which I called it, but I want that as w. And then here I have sine, so I need np dot sine. And then I want to change this to omega. And I want to change this to np dot sine. and then I want to change this to theta. And it's not, I don't need to tell it's a function of time because NumPy doesn't understand that. And that's that. Oh, I think that. Wait. Yeah, that's right. Okay, so I have theta double dot. Now I can update theta dot equals theta. This is just like before. Theta equals theta dot plus theta double dot times dt, and then theta equals theta plus theta dot times dt, and then t equals t plus dt. Now I need to add those new values to my plotting list so that I can plot them. So tp equals tp plus t, and if you want to do append, you can do append. I like it this way. You do it your way, I do it my way. Theta p equals theta p plus theta, add it to the list, and that's that. Now I need to plot it. So let's go ahead and plot. To plot, I'm going to say plt.plot tp theta p. That's going to plot tp versus theta p. Now there's some parameters we want in here, so let's go ahead and make it a little bit prettier. So plt.xlabel, label, t in seconds. Plt.y label, theta in radians per second. No, just radians. Yep. And then plt.show. Let's just see if that works. Nope. Yeah, because I misspelled y label. Label. There you go. Looks pretty much the same. I'm pretty sure it is the same. And there you go. So we solved it two ways. And again, you know, you can debate whether you like NumPy better and Jupyter or WebVPython, and you're wrong because I like WebVPython better. Just because of the animation stuff. And you can actually do WebVPython in Jupyter. I find it's a little, doesn't really like to behave. It does not work on, last I checked, Google Colab. You couldn't load that module. But the important thing is this stuff up here. How can we solve? This is not too bad, right? How can we do a symbolic solution of a problem that's very difficult? Because you can imagine that I could get very, very, very difficult problems and the algebra could get messy. And in particular, look at this. Let's go back to the board. Here we are back at the board. Okay, now imagine that I have a different problem. What if I change this so that it does this? What if it oscillates back and forth in the x direction? That's not too difficult to fix, right? I just need to change this value. It's going to be plus a sine omega t, and that one's not going to have that. And then if I change it in my Python code, I'm pointing to my computer right there, it would just be the same, almost same code. I'd get a different solution. I'd get a different value for theta double dot. But the Python stuff would be pretty much the same. Or what if I did something cool like make this move in a circle, the pivot point? Okay, so all those things, you're going to set it up the same way. Now, there is the problem of what happens if I have to deal with more than one variables. You have to do some different stuff there, but I want to just do that at a different time. So, okay, that's that. Talk to you guys later.